Hello and welcome back to Differential Equations section 2.7 Electrical Circuits. So we're going to take a look at another application of our constant coefficients, second order linear differential equation with or without forcing. Now we're going to use with forcing because we will have source. We're talking about electrical circuits, and we first look at our diagram here, which contains source, which is this circle with a squiggly line inside, signifying that we have alternating source, which would be some kind of sine and cosine, and then for alternating currents. And then we have a switch that we can open and close. We have a capacitor, inductor, and resistor all connected in series. They all share the same current in one loop, and each one of these components connected in series will have its own voltage drop. So when you add all the voltage drops, you get the total voltage for that circuit. Now, our voltage 1 is the voltage that we assign to a capacitor, and the capacitor voltage is going to have 1 over capacitance times the Q. Q is charge. So capacitors get charged, they store electrical energy, and then they release it when it's necessary. So 1 over C times Q. Voltage on the inductor, our V2, is L times di dt, which is the inductance times the change in current over time. Now these are definitions that you need to know if you want to set these things up. And finally, the resistor is just the good old Ohm's law, which is the current through times the resistance, which is given in ohms. Yes. Di dt, the time rate change of current. All right, so now if I use this in conjecture with the voltage drop equation, I see that the equivalent voltage, which is our source, E of t, is going to be the voltage on the capacitor, which is 1 over C times Q, plus the voltage on the, what was my next one? Inductor, which is L di dt, plus the voltage on the resistor, which is IR. So we add all of these guys up, and we have our equation for the voltages. And now, what I didn't say is that the change, what is current? I never defined the current I. Current is the change of charge in time. So dq dt. Yep. Change of charge in time. So current is the change of charge in time. So you have the flow of current through the wire or through resistor. So now you get to plug in this I into these two locations. We get E of t is equal to 1 over C Q plus L second derivative of charge over dt plus R times dq dt. And I hope that you see that you get the second order differential equation with constant coefficient. You have L Q double prime plus R Q prime plus 1 over C Q equals E of T.
So what we did was, what's that letter after LD squared? Near the squared?
Q. It's LD squared Q over NT squared.
You plug in. Now, there is a better form of this equation that is in terms of current. For alternating, right, because we know that the change in Q is I, right? The change in Q is I. If I differentiate this one more time in respect to T and do the substitution, what we are going to get here is L. Let me write it as a first what we get. So if we differentiate one more time in respect to time, this is what we get. But then if you write it out, you will get the second derivative of dq dt. Right? This is the third derivative actually, because you have d squared and then d. That's d cubed, right? So it's third derivative. Plus r d dt of another dq dt plus 1 over c of another dq dt is equal to e prime, which is the source. Now do you see that each dq dt, dq dt, dq dt? What is dq dt? I. So we have the second derivative of I plus the first derivative of I plus 1 over c times I equal e prime of t, which gives us the equation that we actually like to use. And that equation is Li double prime plus Ri prime plus 1 over c I equals e prime of t. And that's the equation that we want to use for electrical circuits. So you have one for charge, but you also have one in terms of the current. It's the same equation, just in a different variable.
I went to one meeting and I was very unimpressed.
All right. So let's take a look at a problem. They're all.
It's just like the word problem that we got in the test, the mechanical one.
Mechanical, yep.
It's the same thing.
So this is what we have. Consider an RLC circuit, which is the circuit that we have, resistor, capacitor, and inductor, with R equals 50 ohm. Yes. This is just example one I want to go through real quick. 0.1 henries and capacitance is 50 millifarads. Wow. So 5 times 10 to the negative 4 farads. At time t0, so I0 and Q0 R0. That's initial condition, guys. And the circuit is connected at 110 volts with a 60 hertz alternating current. Guys, that's your outlet, regular outlet. So find the current in a circuit and a time lag for a steady periodic. Let's just find the current for now.
We're going to be using code and sine, correct? Because this is on here, correct?
Yes.
You left out timeline. It's going to be a little bit more confusing. Can you look at what you're talking about?
No, I talk about this is phase shift. Yeah.
How do you know it's alternating current?
I'm not sure. Well, I'll take a look.
Yes.
All right.
60 hertz, which is a frequency.
So now we have a frequency, right? We have frequency. So our frequency is 60 hertz. And from frequency of 60 hertz, we can calculate the omega. If you remember, the way the equation works needs to be cosine of actually no, 0 and 0. So this one sine. So it needs to be sine omega t. Now sine omega t, we have to calculate omega first. We have frequency, that's not omega, right? And we also have to calculate the amplitude, which we'll use the 110 for. So when you are calculating the omega, which is the circular frequency, you have to multiply by 2 pi for the entire revolution, right? And you have the how many changes you have. So to calculate omega, we have 2 pi times 60, right? And 2 pi times 60, which is 120 pi, which is approximately, stealing the number, 377 radians per second. So we have our omega. So now that I have omega, I can plug that into my source. The source in time is going to be 110 volts, that's the amplitude, times the sine of 377 times t. But we need, for our equation, we need E prime. So we have to differentiate this puppy. And we have 377 times 110 times cosine of 377t. And what is, when we multiply this, we get a number. 377 times 110, yes. Cosine 377t. All right, so now plug everything in. L is 0.1, so 0.1 I double prime plus the next one is R, which is 50 I prime plus 1 over C, so that's 1 over, what was the capacitance given? 5 times 10 to the negative 4 times I is equal to 41,470 cosine 377t. I don't care how awful these numbers are. This is a constant coefficient equation. You solve this using 2.4. Whether you're going to use variation of parameters or you're going to use your undetermined coefficients. It's going to be solved using that, right? So if I... Well, hold on. So we have 0.1 I double prime plus 50 I prime plus 2000 I equals to 41,470 cosine 377 t. And now, remember what you...
The 1 divided by 5 times.
1 divided by...
Wait, it flips up, it's the same.
Yeah, exactly. 10 to the 4 goes up as 10,000 divided by 5, you get 2,000. Yeah, good. So
see that. So what we have to do is factor in.
we do nothing new.
Yeah.
What's new is the setup. Setup is new. And this thing is just replacement there. So now you factor this, use the quadratic formula. Now in my, oh no, I just, you know, these things are communicated to me, so R is equal to yeah, it's 44 and 456. So no, I got this. Trust me. Minus 4 times is 800, right? Divided by 0.2. Because this is going to knock off a 0. That's 200 times 4 is, yeah. See? .2. So we have negative 50 plus minus 41.2 divided by 0.2. Multiply by 10 to get rid of the decimal on the bottom.
Is it 41.2 or is it 42? Oh. Oh, that's what you did.
Magic. So we have negative 88 over 2, which gives us negative 44. And when we subtract these, we get negative 912 divided by 2, which gives us negative 456 as I have foreseen. So the current, and this is the H part, right, for the homogeneous, is C1 e to the negative 44t plus C2 e to negative 456t. And now is the time for us to do the let's do the variation of parameters, right?
Yeah.
Variation of parameters better? Yeah, that's the spirit. Who can tell me variation of parameters formula?
Oh, I think I can.
You think you can?
Okay, so negative y1 times the integral of y2 times f of x over the Wronskian dx
Nice, you got it.
plus y2 integral y1 times f of x over the Wronskian dx.
Boss.
Of all the formulas like we've been doing for the last many years, this is probably one of the easiest to memorize. Like, there's just so much logic to it that it just clicks.
Well, good for you. I still
Nice.
gotta work at that.
So this is going to be our IP. Need a Wronskian for this one, right?
Oh no, maybe.
Yep. Welcome to the Matrix. W. Sometimes it doesn't sync and it erases it. So now we have negative 456 e to the blah, because it really doesn't matter, because they're going to plus 44 e to the same blah. Oh no, we need that blah, actually. So that's going to be when we add, ooh, it's 500. Right?
Yeah.
Well, that was easy. So when we subtract this, it's going to be negative 400 and then 1 and 2, so 412 e to negative 500t, and that's the Wronskian as a function of t. And now it's time to plug everything into IP. So negative y1, which was e to the negative 44t, integral of e to the negative 456 t times the function.
Some big number sign something.
This is the time when you start regretting that you're alive, right? 41770 cosine 377t divided by the Wronskian, which is negative 412 e to the negative 500t dt, and then plus e to the negative 456t integral to the e negative 44t, lock the doors, times 41770 cosine 377t divided by, guys, please work this out on a napkin for someone when you go out, minus 500t dt.
No, we have to lock the doors first, and then you write it on the napkin.
All right. So this is further equal to this. These numbers will hopefully cancel. So 41. 4147. Thank you.
Oh boy, that envelope description looks so great.
So it's about 100 e to the negative 44t integral. All the constants are out. Now these guys subtract, you get e to the positive 44, so e positive 44 times the cosine of 377t dt. That looks more civilized, right? And then you have the same constant kick outside. Again, I rounded this because it was actually 100.65, but yes. So minus 100 e to the negative 456, details. T integral of e to the positive 456 cosine 377t dt.
Where do you find the 100?
When I divide the numbers.
Oh, okay. Where did the T and the exponent B go?
Where?
Where did the e to the negative 500t go?
You combine the e's by adding or subtracting by subtracting their exponents.
So that's why you got e to the negative 460.
Yes.
Makes sense now.
Of course, it's math.
I get what you're saying. This is actually easier than I thought.
Well, wait, now we have to integrate this.
That's bad.
You remember how to do this integral?
No.
Yeah, integration by parts twice, and then move it. Yeah,
This would
yeah.
be one of the problems that I skip and go to a like just replace.
He's gonna make it work.
What do you want?
He's gonna put another problem like this.
What happened?
Yeah, to integrate that B4 to the 456t cosine.
Yes.
377t.
So we now integrate this, and yeah. And once you figure out the integration for these, then you have your full solution for the current. Now let's integrate this. Integrate like a boss.
You learned one thing. Redo this problem like 80 more times until you get it in the test. To the point you remember.
So what are we integrating, guys? Can anyone read the first integral without the obviously 100e something in front? So just, what is it? It's e to the negative.
I think the 44 is a positive.
Negative 44
That's the wrong thing.
t
And then I forget what happens after that.
times cosine of 377 t.
I'd be totally honest with that.
Boom.
Oh god, look at that. Yeah, that's what I thought it was. Bad.
Is that the answer?
That's one. Is it the positive 44t?
Why? Oh, who said negative? The first one is positive 44, and then the next one is positive 456.
Oh, I got half of it right.
So now,
So you just changed that right there. Now you got a
yeah, I know, but now Wolfram has to, you know, use the service again. to recompute.
Look at those amplitudes. Those amplitudes look nice.
No. It's just easy. That was beautiful right there.
But that's only one part of it.
That's the beauty of this.
Yeah, that's half of it.
Yes. This is half of the integral. We still have to multiply this by e. That is in front of the integral, right?
Yeah.
You still have this 100e that you have to multiply into this thing.
All right. But what about the e to the 4?
So
That's a different.
so now we say
I know we have to integrate that, right?
Wolfram this, and then finally we have the answer. And the answer is going to be C1 e to the negative 44t plus C2 e to the negative 456t plus Wolfram stuff.
But you gave us initial conditions, didn't you?
Exactly.
So we got to figure out what C1 and C2 is. Oh man.
Now you get to differentiate this to get your Q,
Oh god.
and then you plug in initial conditions to find C1 and C2, and then you are able to start learning about electrical circuits. So this is how the cheapest, straightforward problems in EE look like. This is just one massive mess of calculations were the principle, guys, is the same as the problem we had a few sections back, where we just were able to factor and not worry about, you know, insane functions and insane constants. But I will argue that this problem is not harder at all than any of the basic problems we did with numbers 1, 3, and 7. The only thing that it's a problem here is that you're dragging these huge numbers that you are reluctant to write. That's all it is. Yes?
Is this one from like the book, or is this just...
Yes, this is example 1 in your textbook for, yes. This is example 1 on page 176, and the lecture started on page 175. So, yeah. They also have example 2, and then they quit.
Wait, then serious? They quit on example 2?
Example 2, and then immediately on 179, problems. And
So even the people
they-
who were in the book said
they write 25 problems on this one, and then they quit that as well. So if you want to be electrical engineer, this is what you do. You go home, you open these problems, and you solve them all. It's going to take a month, but yeah. You'll be doing this all the time.
Or you take circuits and learn quicker ways. Figure this stuff out.
Now use initial condition
Maybe use 2 middle
to determine C1 and C2, which is additional 20 minutes, and you're all set. You're done. Perfect, right?
Yeah, exactly.
Okay. We need another example? Everyone is going, hell no.
Is there even enough time for
Next chapter? Yeah, probably we'll end up the whole. No, next one is power series. The problems are longer.
No. Why?
Alright, so since we're doing one section, one chapter from chapter
Yeah.
3, it looks like we're just going to remember that one on the bus.
So, okay, so that's it for circuits. You plug in values R, C, and L where they belong, and then you crank constant coefficients. You will necessarily have these crazy numbers, but it's not going to be anything out of the realm. We didn't learn anything new in terms of differential equations tonight. We'll just applied the procedures. So that ends this part. Bye.